Hello everyone, my name is Aryan and today I am going to discuss first criteria of a good estimator. As in my last lecture, I have mentioned the criteria of good estimator. Okay, so in today's lecture, I have considered first criteria. First criteria is unbiased. Okay, unbiasedness. So firstly, before starting the unbiasedness, I'm going to discuss few basic things. Now you can see here any function of the random variables x1, x2, xn that are being observed and t function of x1, x2, xn is called statistic. Is it clear? That means function of sample observation is called statistic. Clearly, statistic is a random variable. Is it clear? I have already mentioned this thing in my last lecture. So if it is used to estimate a unknown parameter theta of the distribution, it is called an estimator. A particular value of the estimator, that is t of small x1, small x2 up to small xn, is called an estimate of theta. Okay, so this is the basic concept. That means we have a statistic, and if we are using this statistics for any population parameter estimation, then it's called estimator, and particular value of the estimator for any particular given set of observation is called an estimate of theta. Okay, so this is the basic concept of estimator, statistic and estimate. Now come to the definition of unbiased estimator. Now you can see here, let x1, x2 and so on xn be a random sample from a population or from a probability distribution whose probability either mass or density. That means if we have discrete random variable, then consider mass function. If we have continuous random variable, consider density function, is fx theta, which depends on a parameter theta, and theta belongs to parameter space. Okay, so this is the basic things which I have considered here. Now come to the next thing. Let capital T be a function of observations, that is T be a statistic based on NIID random variables x1, x2, xn with probability function fxi theta, and T be an estimator of theta, and capital T is said to be unbiased estimator of theta if mean of its distribution is equal to theta. That is, if expected value of t is equal to theta for all theta belongs to parameter space, so this property of an estimator is called unbiasedness. Is it clear? That means we have considered here x1, x2, xn be a random sample from any population or from any probability distribution function. So if we have t, an unbiased an estimator, and if t is an unbiased for any population parameter theta, then this condition should be hold. Expected value of t is equal to theta. That means mean of its distribution, mean of its means mean of capital T distribution is equal to theta. This is expected value of theta. Is it clear? Okay, so this is the definition of unbiasedness, and come to the next thing. Okay, so if T is not an unbiased estimator of theta, then it is called biased estimator and defined as bias of theta is equal to expected value of T minus theta. That means the difference between mean of the distribution of T minus the value of the parameter is provide us the bias of parameter. Is it clear? So bias may be positive or may be negative. If expected value of t greater than theta, then the estimator is said to be positively biased, and if expected value of t less than theta, then it is called the negatively biased. And if limit n tending to infinite and expected value of t is equal to theta, then t is called asymptotically unbiased estimator of theta. Is it clear? So here I have mentioned three concept of uh, first one is the biased positive bias, second one is the negative bias, and third one is asymptotically unbiased estimator. Okay, now in general sense we can define unbiased estimator like this, because in my previous lecture I have considered gamma theta as a parameter. Okay, means function of parameter. So in general, if expected value of t is equal to gamma theta for all theta belongs to parameter space where gamma theta is a function of theta, then t is said to be unbiased estimator of gamma theta. Is it clear? This is the concept of unbiasedness. Okay, so that means if we have any estimator and the expected value of that particular estimator is equal to value of the parameter, then estimator is called unbiased estimator. Okay, so now okay, so now come to the numerical problem based on unbiasedness. So first question is, so that summation of xi into summation of xi minus 1 upon n into n minus 1 is an unbiased estimate of theta square for the sample x1 x2 xn drawn on x, which takes the value 1 or 0 with respective probabilities theta and 1 minus theta. Okay, so this is the question based on the unbiasedness. And come to the solution part, how we can prove that the given value in this quantity, or we can call it statistic, is unbiased for theta square. Okay, now come to the solution part. Since x1 x2 xn is a random sample from Bernoulli population with parameter theta, why we are writing Bernoulli population? Because in question mentioned that x which takes the values only 1 or 0. That means we have only two possibilities. That means this is the case of Bernoulli distribution with respective probabilities are theta and 1 minus theta. So that x1 x2 xn is drawn from Bernoulli population with parameter theta. That is the probability mass function of probability about Bernoulli distribution is theta to power x into 1 minus theta to power 1 minus x, and x takes value 1 and 0. Okay, so now we can write capital T is equal to summation of xi. That means we are just taking summation of xi is equal to t. And we know that if x follow Bernoulli distribution, that means x1, x2, xn follow Bernoulli distribution, then summation of xi will follow binomial distribution with parameter n and theta. Is it clear? Okay, so this is by additive property. So I'm not going to show you this result. Okay, now, so this is the probability mass function of binomial distribution with parameter n and theta, and we are taking capital T is equal to small t. So nct theta to power t into 1 minus theta to power n minus t. And we know that mean of the binomial distribution is what? N into probability. So probability is theta. So mean is n theta, and variance is what? N into theta into 1 minus theta. Is it clear? So now by definition of the unbiasedness, we want to prove that this expected value of this quantity is equal to theta square. Now, by the definition of unbiasedness, we have expected value of this quantity is equal to theta square. Okay, so now just simply we are taking capital T is equal to summation of xi, and we are rewriting this term in form of expected value of t into t minus 1 upon n into n minus 1. And after simplification of this term, what we are getting? 1 upon n into n minus 1 is outside, and first term is expected value of t square, and second term is expected value of t. Okay, and now we know that the formula for the variance, and variance of t is equal to et square minus et whole square. So in place of expected value of t square, what we are writing? Variance of t plus expected value of t square. Okay, and second term is minus expected value of t, and we have the value of variance of t and expected value of t. So after putting the value of variance of t and expected value of t, we are getting the next step. Now you can see here. Okay, so now after simplification, now you can see here first term is n theta and minus n theta square plus n theta square minus n theta. So this n theta and n theta cancel out, Now we can take n theta square common in both terms. So it becomes n theta square into n minus 1, and in denominator is n into n minus 1. So n minus 1, n minus 1 cancelled out, and n cancel out. The resultant is what? Theta square. Okay. So is it clear that the expected value of summation of xi into summation of xi minus 1 upon n into n minus 1 is equal to theta square? That means this is an unbiased estimator of theta square by the definition of unbiasedness. Is it clear, guys? Okay, so if we have any problem based on the unbiasedness, so we can proceed the similar way and prove that the given estimator is unbiased for any particular parameter or not. Okay, so thank you so much to everyone for watching this video.